Yeah. So let's look at another problem. So let's call it problem 2. Problem 2. So you're asked to solve 2y dx plus 2x natural logarithm x negative xy, the y equals to 0. Understand 2x natural logarithm x. So we have this question, problem 2, 2y dx plus 2x ln x minus xy, the y equals 0. So solving this problem, let's call m to be 2y, and let's call n to be 2x ln x negative xy, such that the y equals 2, and the n dx equals 2x equals 2 ln x, 2 ln x plus 2 negative y. Right. So we could see that since the y does not equate to the n dx, so this means that it is non-exact. We good? So now we've come to another step. The first one we did, it was exact. But now we are having a situation where it is not exact. The reason why it is not exact is simply because your partial derivative of m with respect to partial derivative of y does not equate to partial n, partial y, and partial x. So the next thing we have to do now is, since it is not exact, then we need to find integrating factor. And our integrating factor, now, one of the things that I always used to tell students is this. One of the things I always tell students is that in order to solve this kind of problems, what do you think? How do you think you should structure your integrating factor? Or what do you think will determine your integrating factor? Mhm. Yeah, exactly. The bottom factor. Now, the bottom factor have to be decided rightly, depending on the numerator, right? So that's good. That's very intuitive of you. So what do you think will be our bottom factor here? Why? Exactly. Exactly. So this is one of the things I always used to tell students. You should know, because it is two cases. There is the first case. There is the case one. The case one is when you have the m, the y, right? The n dx over n. So in these kind of cases, you will have your, possibly you will have your, mm, you will have your integrating factor. No, you will have your, wait, it will be exponential of this. This might give you a function that is y only. Do you get what I'm saying? So this will give you a function that is y only. That what I mean by y only is it could give you 1. it could give you y. It could give you y squared when it is done rightly. So y only. You know y raised to 0 is 1, right? So it's still a function of y. So that's the first case. The second case is where you have to choose, probably you have to use the n, the x minus the m, the y over m. So this should give you function of x only. X only. Can you tell me what that is using case one? Using case one. So I'm using case one. So I'm using case one. So I think this is x only, sorry. X only, then y only, right? Yeah, x only, x only, y only. Then the third one is that. So using case one, you have the m dx, the m dy is what? 2 negative 2 log or 2 ln x, whether you write log x or you write ln x. Yeah, plus 2, minus y. Now we are using that because of our n, which is the bottom value. Then you have 2x log x minus xy. So do you see why we are using case one and not case two? We're using case one because if you evaluate, maybe sometimes if you want to do it, it is okay to be confused of whether to use case one or case two. I think it's fine. You can decide what case now to use by first try as much as possible to evaluate the top value. When you evaluate the top value, then look at your m and your n and try to see which one can try to divide each one out. You cannot tell me that you will use case two, because after evaluating this problem, you are having something like this. Let's say you are having something like this. If you evaluate, this is negative 2 natural log x. So I'm just interchanging them. And I'm having plus y all over. So you can tell me that if you're having a top value to be in that form, you cannot tell me you'll be using m, right? Because m is just equals to 2y or 2. So there is no way you can use 2y because it doesn't make sense. So that's why then you can conclude I'm using case one, because I know with n being the numerator, the denominator, I can be able to make that evaluation correctly. And also the way you place it determines whether you have negative or you don't have negative. So you should be careful. It's not just about, so if you at the start, maybe you were using maybe at the start you don't know which one to use, and you did the partial m partial y minus partial n partial x, right? And when you did that, you concluded that no, I think I should use case two. What you just need to do is to what? Just multiply what you've had already with negative. From here, I can rewrite this to be x 2 ln x minus y, right? This cancels out this one, and this gives me what? Negative 1 over x. This means that I have, this will be minus negative x. So after this, you need to obtain your integrating factor. You can denote your integrating factor as mu equals to the integral of negative 1 over x dx. And this will give us what? Yes, e negative nx, and this is 1 over x. And so this is our integrating factor. The next thing is to multiply your integrating factor with the problem, the initial problem you have, this one here. And that will give us what? So multiply it with equation. Let me call it equation star. Now multiply, let me call this star star. Yes, just a minute with star. Okay. Uh-huh. Mm-hmm. Equals, thank you. Now we've gotten a new equation or a new expression. So you have to restart. It's just like you are doing your numerical iterations. It's just like you are doing iterations. Maybe you are using Euler method, or you are using Newton's method. You know, when you get the first iteration, you use the same approach, but now on a new set of equation, right? That's how you do. Then you get the next one, you get the next iterations. So this is exactly how you will do here. You need to now apply the same method of obtaining whether it is exact or not. Then you need to apply it again to your new generated equation.